and all of that. Now, because of me screwing up, what was it? The progress check last unit. Some of you have already taken this, so that might be a really easy Friday for you. So just know that that was my bad. Either way, it still counts. Any questions about this week? Oh, and that means Monday will end up being your unit test.
Okay.
All right.
The team's meeting for the AP shirts, when's that?
So that I emailed anyone that had mentioned to me before that they were interested in creating shirts for this class. We did last year. They turned out pretty nice. Would you guys be able to meet today after school? I'm working on the page right now. That way we can get like some jobs and figure out what we've got to do, things like that, like right after school. All right. And hopefully, Daryl, you stopped summoning transformers. We don't need those. All right. So go ahead, open up your packets if you don't have any questions. And we'll try and finish this one off. And where is it? Make sure. Okay. So the packet, you can turn it in anytime this week. I usually like to have you guys turn them in around progress check time, because you can use your notes and whatever on the progress check. So the only issue is there are a couple people doing them on paper. So this end of this week, beginning of next week, whenever I see you after the progress check. All right, sounds good. And I do have the next unit all ready to go. Why does it say my name up there? Okay. Oh, I totally screwed that up. All right, so in your packet, there should be a part. I'm going to turn off one light. Hold on. Okay. So in your packet, I'm just going to put them all up here because it's easier. That's not annoying at all. See if that goes away. Apparently not. Does that work? Nope, that doesn't work. All right. Well, we'll just have to deal with weirdly functioning technology. All right. So sometimes yesterday, I'm just going to back up just a little bit. I'll come back to this slide. Not yesterday, Friday, we talked about different things like producers, consumers, detrivores, carnivores, things like that. So sometimes within that food web, I don't know if you guys noticed it when you were working on your biomes project, that you have overlapping terms for the same animal. So for an example, a sea turtle can be a predator, it can be a heterotroph, it can also be a secondary consumer. They all mean different things. Secondary consumer means it's eating primary consumers. Heterotroph means it has to eat to get its food, to get its energy. Predator means it's attacking other animals, not plants, animals. So lots of different names for the same exact thing. A gorilla is an omnivore, so it goes meat or vegetarian. Predator, heterotroph. And the last one on there is a pillbug. I heard another name for those the other day, and I forget what it is. Pillbug, detrivore, consumer, omnivore. So even though they occupy different parts on a food web or a food chain, they can be termed with different meanings. All right. Am I good to go?
Yes.
All right. So, there are a couple practice questions in your note packets. All right. Remember, in a food chain or food web, the arrows follow the flow of the energy. This is typically one of the biggest mistakes that students make. So they travel from one level to the next level that consumes it. So you're not saying this that dandelions eat snails. You're saying the energy from the dandelions goes to the snail. Snails don't eat birds, but snails do give their energy to the birds when they are eaten. Okay, so you should have a couple little practice things in there. I'm going to give you a few minutes to go through. You can ask me questions if you'd like. I'm pulling mine up right now. Maybe.
The practice math ones?
Yes, it should be. Sorry, my computer is freaking out right now.
So can we go over the first one?
Yes, if I can get to it. Oh my god.
I think I'd be able to score this, and I'm like, oh.
Oh my gosh. Okay, come on.
You seem as good as how
You broke it.
I did. I've totally broken my computer. Ever since I got this replacement one, it's just been nightmares.
somebody was over.
Yep. That's what happened. The backlight of this computer went out, so they gave me a junior. It was horrible.
Yeah, I have one of the
It
senior
died.
laptops. Yeah.
Died at half battery.
There we go. I'm almost there. All right. Finally. Okay, so this is what you're working on right here. It says use the table to the right to draw a 4-member food chain and the levels of consumers. So the hint is to always start out with something that is photosynthesizing, because that is the bottom of our food pyramid, right? What is another word for something that does photosynthesis? There's a couple other terms you can use. Here we go. Here's a couple other terms you can use when you talk about things that do photosynthesis. They are producers. They produce their own energy. Autotrophs. Auto is self. Troph is food, so self-feed. All right. So we always start with that at the bottom of our food chain. I'm going to go back really quick. Okay. So you start out with something that's photosynthesis, and then it tells you what things eat, right? Like you're not going to do the cat next, although it looks kind of blue and it's kind of weird, because it eats mice and birds. So you need to make sure that whatever you're doing, like rotting leaves, they eat worms, and so on. So you're just building your own. And I know if you're not doing it on paper, you can't like draw it or copy and paste the pictures because it's one image, but you can at least type it out. Hopefully none of you have rabbits eating bobcats, because that's not how it works. And then this one is just going into more than the 4. So this is get your basic food chain down, and this is adding the rest of them in. Okay, so that's all you're working on right now. Gonna move on in about a minute. All right, so just as a reminder with this, if we do a paper and pencil AP exam like we would normally do in times of non-COVID, then this might be something you end up having to draw, and your arrows have to go the right way, or it's like 0 points for all your hard work. So do keep that in mind. It follows the flow of energy because that's what we're concerned with. And then, like Leland said in the chat, rabbits only eat bobcat if it's ground up in rabbit feed and animal stores. Not true. Animals are herbivores, therefore they don't have meat in any sort of rabbit feed. So you'll have to kind of know some basics of what's an herbivore, omnivore, things like that. Typically carnivores are the top of your pyramid. All right. Oh, let me put the, come on, there it goes. Okay, so with ecological pyramids, I know you're kidding, Leland, it's fine. Graphical models of the differences between trophic levels of a single ecosystem is typically what they represent. An energy pyramid, also sometimes called the trophic pyramid, which is kind of what we looked at, excuse me. There's also a biomass pyramid, and then there's a pyramid of numbers.
Numbers in the environment.
I know, crazy. Pyramids, like the picture and the term implies, become narrower at the top. So when we looked at that, how many, what was it? How many like bugs feed the frogs that feed the salmon that people eat in every year? And you're in the hundreds of thousands. That is what it means by it gets narrower at the top, is that it takes less organisms to consume anything below it. Hopefully I didn't confuse you even more. All right, so pyramids of energy. I'll put the rest up in a second. We've talked a little bit about the 10% rule. So whatever you have at the bottom, 10% of that energy is what moves up the pyramid. Come on. I'm going to put all this up. There we go. So 90% of the energy from, let's say, a producer to a rabbit, so some plant to a rabbit, is completely lost in that transfer. It goes out through fiber, it goes out through heat, and other processes. It gets not used as energy. Conversion efficiency is the ratio of net production at one level to that of the next. And sorry that cuts off. I don't know why it's doing that. No clue.
Your text box wasn't big enough.
Well, it shows up fine if it's on any other screen but my projector. Because usually the PowerPoint covers the start bar, and this time it won't, and I don't know why.
Oh.
Yeah.
No idea then.
Stupid technology. All right. Pyramids of... There we go. Pyramids of energy is really a way to show loss. Like I was saying a little bit with the last slide, you lose some of it out as feces, especially fiber, urine, respiration, and heat. That's pretty much all where it goes. So you can see the 10% rule here. If a meal of grass has 1,000 kilocalories, then that grasshopper only gets 100 kilocalories from it. What eats the grasshopper gets 10 kilocalories, and then this owl at the top, who's a tertiary consumer, is only going to get 1 kilocalorie out of that original 1,000. So that is the 10% rule and how it works. All right, next one is biomass pyramids. It's the total mass of organisms. The missing mass, which you'll see a little bit here in a second, that is not eaten becomes detritus and composed. And honestly, usually your detritus and decomposers usually get left off a lot of the pyramids because they can kind of jump in at almost any step. So they kind of just get put off to the side. There we go. So this is a little bit more of what like a biomass pyramid would look like, measured in weight per area. So grams per meter squared is an example, or kilograms per kilometer squared. Again, you have your producer, your primary consumer or herbivore, your fox, your secondary consumer, your wolf, your tertiary consumer. So this shows biomass, and hopefully you guys are all comfortable with scientific notation.
Maybe 2 years ago. I haven't done scientific notation in 2 years.
Oh, lovely. All right, pyramid of numbers. So this just kind of gives like the numbers of individuals at each level. It still has to be in pyramid form. So for 3 tertiary consumers like the wolf, you would need over 5 million, almost 6 million producers in that environment in order to support 3 wolves. So that is part of that 10% loss. If our pyramid starts going upside down, it's not good. All right. Maybe. All right. So pyramids of numbers, you can see them done a few different ways. Pyramid A shows a typical pyramid for a terrestrial system with small producers like a grassland, which is why you have grass, the snails eat the grass, the mice eat the snails, owl eats the mice. Pyramid B shows the effect of a single large producer, such as a tree. One tree can support a whole lot of caterpillars, and then the caterpillars support the birds. Yes, this is not a great pyramid, but this is just a very specific looking at a single thing of how much that producer can handle. Obviously, hopefully there's more than one tree. But look at the biomass difference too, like the size of an average pine tree versus the size of a caterpillar. C shows what a typical parasitic food chain would look like. So you have parasites that would eat aphids, that eat a rose bush, or the leaves. So it's definitely upside down because they're parasites, so they don't care. All right, so inverted pyramids. So notice how in different ecosystems, season differences can all lead to different shapes of pyramids. So you can get these inverted pyramids like you just saw on the last screen, or these ones right here. Typically, you're going to see them with numbered pyramids or biomass pyramids, like the tree with the caterpillars. You're not going to typically see them as far as the amount. All right, next one. Oh, I forgot about that last one. These pyramids also result from seasonal fluctuations, your migrations, things like that, as well as natural disasters can completely wipe a specific part of that pyramid out and create an upside down one or some sort of inversion, something weird. All right. Can an energy pyramid ever be inverted? Think about that before you answer. And tell me why.
No, it can't be.
Why not?
Because anything that eats it is only getting like 10% of what the other animal had.
Okay.
And it'll always be like that.
Using this horrible looking building. Good, Dante. There isn't enough population down on a producer level to support that many. Imagine this entire school having to share one head of lettuce for lunch. That would be bad, right? That's not going to help us out. So there's not enough to actually support that system when it comes to energy with that 10% rule like Leland and had mentioned. Good. All right, how are laws of thermodynamics relevant? So I had this originally as a group activity. You guys can work as a class, you can work as a group, you can work individually. There should be a link to this article and being able to build a food web from this article. Oh, I accidentally clicked really fast. I just did want to say there's 2 laws of thermodynamics that come here. Energy cannot be created nor destroyed. There's always going to be less energy as you move through the pyramid. It gets converted into other types of energy, like heat being one of them. Sorry, totally skipped that. All right, so we've got just under 20 minutes of class left. You'll have time to work on this. You'll have time to hopefully finish up this stuff. If my computer would work, that would be wonderful, instead of freezing all the time. I'm really feeling Daryl and Ashley's pain right now. These computers suck. So that's what I'm giving you guys the rest of time to do, even though I can't scroll, apparently. There we go.
Put these right here. For purposes of can you go over the first one?
If I could click on anything, I would love to, but it might be a minute.
Okay.
Oh, Lord. Okay. I'm getting there. All right. So you have a food web up here in a little triangle. If it helps you to separate out, I think it would be to put like the grass and the alfalfa down here, the grasshopper and the rabbit, and then the mouse, and so on. So this gives you kind of some conversion units. So you could think of this instead of like a farmer lives off 1 chicken per day for a year. That's kind of like 12 inches in a foot. Like they're just conversions. All right, so calculate the number of beetles a chicken needs per year. So, I need to make this bigger because I can't read it. It's blurry for me. All right, so we have a hen that eats 20 beetles per day. And that's the only one that we have to work with right now. So that is per day, and we need per year. So there we go.
20 times 365.
Yep. Keep the leg on this.
7,300.
7,300. I'm going to trust you are correct.
I mean, yeah, I use the scientific calculator. Can always trust them, you know.
Well, you say that. Wait till we get to population stuff. Okay. So that's all it would do. So 20 beetles every day for 365 days in a year. That means that that chicken or that hen needs 7,300 beetles per year to sustain. So that's literally all you're doing is using these conversions and knowing where they sit on this pyramid in order to answer some math questions. So it's not meant to be like calculus. Okay, I would run away if it was calculus. That's the only math class that has ever given me nightmares. But so that's all you're doing for this. So again, you've got the rest of the class period. You can ask me questions. I can try and go over them if my computer wills it to be. There we go. And don't forget, at the end of every packet is a mini practice FRQ. Normally there's like 10 questions. I only put 2. So be nice to me. Yes, let me write you a pass really quick. Okay. Let's see. How many beetles are needed for a year's supply of chickens for a farmer each year? I love the wording of these. Just kidding. Don't. So that one, the farmer requires 1 chicken per day per year. So how many does the farmer need every year of chickens? Mm-hmm. Yep, so 365 chickens. And then how many beetles are needed for that supply? So in the previous one, we already figured out that one of those chickens needs 7,300. Now we have 365 chickens. So we would multiply. Yep. And I'm just going to trust your math on that, but yeah.
How would we do number 3?
Number 3.
Total mass in kilograms that the beetles need to feed all chickens for 1 year, when there's 2,664,500 beetles, and each 1,000 beetles is 1.5 kilograms.
So you would multiply. So you've got your number of beetles for
Right.
chickens for each year, correct? And then you have the mass of each of the beetles, right?
Only for 1,000 of them.
So it's per 1,000. So you can divide 1.5 by 1,000 and then multiply by that number from number 2.
Okay.
That would be my suggestion. I think that's the easiest way to go about it.
Okay.
What was it, 7,300? And even though I'm not used to it, and you can see me going back and correcting myself, get in the habit of always trying to keep units or labels within some of your numbers. Most likely, like 90% of the time, if you don't put the unit or the label on your AP exam when you're doing your written responses, you'll lose points for it when that's all you had to do. Yeah, what's up? Yes, let me write you a pass really quick. Mm-hmm.
And we turn this in like the end of class today or tomorrow?
No, you have the week to work on it.
Oh,
And
okay.
make sure it's completely finished. I have it set. I accidentally clicked in here. If it loads, oh my god. So I have it here as due on Friday, but you can turn it in. If you finish it Thursday, you can turn it in.
Okay.
Finish it today, you can turn it in. Oh my god. Computer. Okay. So yeah, so it's just there for whenever you finish it.
Okay.
Yeah. The what? Six. Number 6 is something.
It says they eat 3,200 calories a day, and then if he only eats lima beans instead of chickens or beetles, how many people does lima bean cook feed? And it says to go based off your response to question 4. So question 4 answers lima beans needed to feed all the beetles.
Right. So you're going to compare that number that you got for the beetles with the how many lima beans for a person, and tell me why or why not that's sustainable. Does that make sense?
So compare number 3 and number 4 answers.
Number
3 is beetle needed to feed all the chickens.
So that is mass of the beetles. Number 4